Good afternoon, everyone. So I'm very happy to be here, and I would like to thank the organizer for giving me the opportunity to speak. So I'm going to tell you about the Supernovae BAO and GRB cosmology to tackle the Hubble constant tension. So this is work that has been done with many people, and some of them in the room. So we have been thinking and speaking about the Hubble constant tension, and many discussions have been ongoing in these days, whether this is real to new physics or there are still some selection biases or some evolution that we would like to actually tackle, and what could be the answer. So in the past, collaborators and I, we worked on this analysis, and currently we have built the collection of samples of supernovae that I will tell you in a moment. And the point here is that we would like to try to understand what are the implications of the analysis when we consider binning data. So you may remember this plot that it is dear to all of us from Di Valentino Said et al. 2025. And then I have another plot that it is a little bit more messy, but it has more probes. And I would like to point out this because there are also the one in brown and the darker brown that are in relation to GRBs and gravitational wave. But maybe if I can point with a pointer. So yes, I think it's. Yeah, I can probably do the laser pointer or the pen, and it should work. Can you see? Okay, if you just see the larger error bars that are on the brown and great brown, these are quasars and GRBs, and then this is the very large one you have with the gravitational wave. So this is just to show you that after many years, we are still back in the game from 50 to almost 90 with the Hubble constant, if you consider many probes. So we really need to work still a lot to try to come up with one value. So also I added this slide because we had lots of discussion in the discussion panel about the trip formula and about the devil, that it is hidden in the detail. So I would like to show you this one that you probably all of you know about the relation between the distance moduli observed and the absolute magnitude, the peak magnitude in B band, the stretch, the color, and the dust galaxy mass correction that Luis also showed today. So this is a functional form, and we can use a similar functional form also for other probes, as we have seen for quasars, but we can also do this for GRB. And I will show you later about that. Now, what we did for the analysis of binning of the data for the Hubble constant, we took the Pantheon sample, and we divided in 3 and 4 redshift bin, and we tested both the lambda CDM and W0WA CDM model, and we found that there is an evolving trend for H0, which is similar to what Katsantzidis and Perivolopoulos found in the same time, but considering the M value. And since M and H are degenerate, basically these results are similar. So we did an exercise. We said, okay, let's see that this evolution is true and intrinsic, and it can be extrapolated at the redshift of 1100, so at the redshift of the last scattering surface. Basically, we have a reduction of the tension if we consider the difference between the Hubble constant that it is given by the Cepheids and one of CMB compared to the H0 tilde that it is basically a 0 point of the Hubble constant if you consider a simple evolutionary function, that it is 1 plus z to the power of alpha, that it is the function that we are considering here, and alpha that you see in this table, basically it is the parameter that for which we mimic the evolution. Here you can see that according to the number of bins, you have several different values of alpha and also several different values of alpha over sigma alpha that are going to tell you what it is the distance between a flat trend, so in which alpha equal to 0 is possible, and a non-flat trend. Now, if we repeat the same analysis also with the W0WA CDM model, basically you have again a reduction of the scatter. And this is independent from the number of bins that you are using. Now, we did this all with supernovae only in the first paper, and then we added also BAO, so we see that the trend still persists, and we also, in this analysis, we varied contemporaneously H0 and omega m, while in the previous analysis we did vary only omega m. And when we consider the W0WA CDM model, basically we have even a steeper trend, and the trend still exists with the example of 3 bins. Now, there are 2 main possibilities, as I said before. Either you have different theoretical frameworks, or you have astrophysical biases or selection effects. I know that many people in the room that they say that they have done everything, but maybe we could be open to possibility to hidden biases that have not been considered and still dig into understand whether or not, instead, if no selection biases are now present, we can actually have modified theory of gravity. We can try the Usaviki model, which didn't work out very well, but we can also have other theory, for example, slow rolling. And from my point of view, it's important to combine multiple samples so that we can have larger statistics. So in this paper that it is current on archive, we have combined the DES, the PantheonPlus, Pantheon and JLA, giving priority to the newest sample. The binning technique that we have used are 3. So we used equipopulation, equispacing, and moving window. So basically equipopulation, it means that in each bin we have the same number of supernovae. Equispacing, it means that you have the same volume, that it is a function logarithmic of 1 plus z. And moving window means that if you don't have enough data in the equipopulation, you are going to take few supernovae that are in the previous bin, few other supernovae in the next bin, and then you build a large sample in the equipopulation space. So with this additional statistical analysis, we could actually overcome the problem of paucity of the data. So, of course, if you wish to add your sample to this master sample list, just let me know, and we can work out together on the follow-up paper. So far we have gathered among those samples 3,789 supernovae without duplicates, and there was a discussion in one of the panel about how to treat duplicated supernovae in one of the samples. Now, the results that we have in this paper are sort of mirroring what were the results in previous papers. So we are checking the ratio of alpha over sigma alpha, and if the ratio is greater than 1, it means that you don't have this flat trend. So this is not compatible with H0 constant, but it is an evolving trend. And so if you do have that, then we checked whether there is compatibility in 1 sigma with the Hubble constant at the CMB, and if yes, we have a diamond sample. If not, we call it gold sample. And if this compatibility, this alpha over sigma alpha, is not greater than 1, practically we don't proceed with the analysis. So in this paper we have 70 cases, so we tried many samples, and then we have a statistical analysis about how many cases have alpha over sigma alpha that it is larger than 3, because it means 3 sigma away basically from the 0 trend. And here are just examples of 3 12 bins in the lambda CDM and WA CDM. Now, I would like to reiterate this concept about the fact that either we have possibility, for example, for the stretch to evolve with the redshift, and maybe this can explain partially this trend. And this is a paper by Nicolas Permutel et al. In 2021. new data also confirms this trend. There was a paper by Wojtak et al. 2023. So this is the population, different population that are showing this trend, evolving trend with the color parameter and the stretch. And also we could introduce the problem that the supernova redshift distribution also imply a long mean delay time between the formation of stellar population and the explosion of some of its members as supernova 1A, and this was a paper that was published long ago in 2004. So, of course, this is something that I'm happy to hear from the community more thoughts about this. But now, this was sort of an introduction to the fact that I want to ask you whether you are ready to look at the tension from another perspective. Okay, so I think you're ready, so I can move on, and we can consider the fundamental plane relation, which is a relation between the luminosity at the end of the plateau emission, which is a flat part of gamma ray burst, the time at the end of the plateau, and the peak prompt luminosity, which is the main event in the prompt emission, which is mainly observed in high energy gamma rays or hard X-rays. So here we see the plane, and we see the several colors that indicate several classes of GRBs. Of course, I'm not going to go into the messy business of the many classes of GRBs and the many population, but what I would like to convey here is that if you consider that the long gamma ray bursts, they come from the explosion of massive stars, then you can consider that this is a more homogeneous population from the physical point of view. Or we also investigated magnetar and accretion onto black hole, but if you consider the physics that is driven is the same, then you can take a more physically homogeneous sample for this correlation. So we are backed up with the physics, then we can move on and consider how this relationship can be actually used as standard disabled candle. So I showed you before the trip formula, and similarly to this, we can consider the distance moduli theoretical and the distance moduli that comes from this relationship, the fundamental plane relation, as a function of several factors. So you can imagine that this time at the end of the plateau emission is similar to the stretch factor because it is a temporal factor. And then you have the flux at the end of the plateau emission and the peak flux in the prompt emission. Those are the two parameters that you see here, including the K correction. Now, if we consider, so we came up with, also we corrected this relationship for selection biases and redshift evolution. So we did all the many tests, the Efron and Petrosian, and also the Pearson correlation test, and we found out that this relation is actually intrinsic to the physics, not due to selection biases from a statistical point of view. And then we proved also with the theoretical modeling that this is the case, this is driven by physics. So then we applied the GRBs together with supernovae and BAO, but we calibrated GRBs on supernovae. Here we have, in this plot, we consider this, but we also had the simultaneous fitting. And in the simultaneous fitting, when we don't calibrate it with supernovae, however, the likelihood that matters the most, it's the one that has a smaller uncertainty for the supernovae and also larger numbers. So because GRBs have larger scatter and they are smaller in number, then they weigh less if we consider the parameters altogether. But I think we should take one step back here, because what are the assumptions of the likelihood? And I think we had a discussion in one of the panels, so I also added more about this in my talk, because we usually assume that the Gaussian likelihood for supernovae, BAO, quasars, and GRBs, but the point is that are they all valid? Well, the answer is no. Only for GRBs we do actually that they fulfill the Gaussianity assumption, but for supernovae, for BAO and quasars, they don't. And now this is the example with the supernovae. Here we can see that with the Pantheon sample, the logistic distribution is going to be the best fit distribution, while in the second panel we have the t-student distribution that is going to be a better fit than the normal. And you can see some deviation from the distribution of the Pantheon and PantheonPlus sample. So, of course, this is also normalized by the covariance matrix. So when we consider this new assumption, then we have actually a reduction of the scatter on the cosmological parameter, which is H0 and omega m. And of course, here we have, in the t-student, we have a new parameter that we need to fit together with the cosmological parameter. So it is clear that we have an advantage when we use the most appropriate likelihood assumption. And so we have a considerable reduction in the scatter by 43% when we consider the logistic distribution on omega m, and 41% for H0. And when we consider the t-student distribution, it's 42% for omega m and 33% for H0. So it's comparable, 42, 43%, around 34% according to the sample that you are considering, according to the variable that you are considering. And we did this exercise both for the flat cosmological models and also for the non-flat cosmological model. And I know that we have been discussing in these days we should go beyond the lambda CDM, and yes, in this paper we actually do that. What it is interesting here is that if you consider all the sample together, and if you don't consider evolution, or you consider a fixed trend for evolution when you do already know the cosmology, or you consider the varying evolution, so the function of the evolution is also varying together the cosmological parameters. In all cases, basically, you have a reduction of this scatter. And the configuration is that we have H0 values that are higher, so the proms combined together, they go closer to the one of Supernovae 1A, so closer to the value of 73. But now, the problem is that I mentioned before that gamma ray bursts have larger scatter, and also we have a smaller sample. So the point is that what do we need to do more to make gamma ray bursts under disabled candle in a way that the intrinsic errors are comparable with the one of supernova. So basically, we would like to ask help to machine learning to reduce the uncertainty on the parameters of the relation, and also to reconstruct the light curve. And by the way, I would like to tell you that, of course, this is not the main topic of my talk, but if someone is interested, this machine learning analysis for light curve reconstruction can be done also for Supernovae 1A. So all this technique has been done for GRBs, but we have plenty of methodology now built in, and we can do this for supernova as well. So if we consider a precision that supernova got in 2011, so basically we have this precision was already reached 3 years ago, because this is the year of the publication, so we are already beyond that. But if you would like to reach the same precision of Betula of 9 years ago, you need to wait another year. But if you want to reach the precision of Pantheon, then you will need to wait 15 years. But this is a very pessimistic estimate, because basically it does not consider the fact that we have improved machine learning analysis, and also we can infer the redshift of more GRBs with parametric inference with machine learning, so this is going to more than double the sample of GRB. So we are going to reach this precision earlier than that. And what else can we do for the GRB cosmology? Of course, not only maybe discovering new relationship, trying to tighten up this relation, because basically if you have the GRBs that are going to be closer to the fundamental plane, then they are going to have, this relation is tighter, and then you can apply with better success for interpretation, for determination of cosmological parameters. But we need to really have this standard set for GRB, so the quest is open for giving some physical ground, more physical backup to this sample. And this is a series of papers that we have been working on for the machine learning analysis, but I'm going to give detail about that in Cosmoverse in Turkey, so stay tuned about that. And what else can we do at this point? Well, and here also with Arianna, Marina Migliaccio and Adria Gomez, we published a paper last year in analyzing the cosmic calibrator, cosmic chronometer as calibrators for the fundamental plane relation, because we have been also discussing in the panels many times if we have, let's say, some problems with Supernovae 1A, we should be able to maybe consider other independent probes and then use those as calibrators. And this is what we did in here. So the interesting point here is that we obtain the similar scatter of the relation that we have when we consider basically the vanilla lambda CDM model, and so the scatter is 0 to 20%. So this relation is currently among the tightest correlation in the literature, so this is an invitation if you would like to open up to the use of gamma ray burst. I'm happy to provide the sample. We have also an extended sample for this analysis. So, and now with Arianna and the group in Tor Vergata, we are actually extending this to add also other high redshift probes. So the story of GRB cosmology actually does not end here. I would say this is just the beginning, because we can also analyze the impact of BAO from the DAISY collaboration. We can leverage the constraint from Shaw's supernovae analysis. We can actually add the master sample analysis to all these analyses that I've shown here and understand what will be the impact for the errors. And as I said, we can improve this GRB redshift prediction with machine learning. Also, and this is a paper that was recently accepted in a Journal of High Energy Astrophysics for interpreting GRBs as black hole candidates, and there was even an interview from the National Geographic Polska for highlighting these results. So we are really toward understanding the physics of these mechanisms. And so the party still continues, because we have also heard our concern about the funding that are going to be cut, but luckily we have also the SVOM mission that will continue as a successor of the SWIFT mission. Is already launched in June of last year, and plus we have the Einstein probe. So all these estimates that I gave you were without the Einstein probe and without SVOM, so we are going to add those as well. And also, of course, I don't have time now to spend too much about the quasars analysis, but we actually reached a precision with the quasars that it is the same as supernovae 1A, the current precision, when we consider a subsample of quasars that have smaller uncertainty on the luminosity, UV and X-ray luminosity. And also, we did a scavenger hunt for quasars to be used as cosmological tools, considering different binning techniques. We were using the Tilson regressor and other statistical techniques, so that the binning analysis is not going to be arbitrary, but as we could have seen in the previous talk, this is the kind of binning was a bit arbitrary, but in these two papers we actually had a long discussion on how we should not depend on the particular binning technique, and that's why we spent 3 binning techniques. We proved 3 binning techniques to evaluate that. And we also actually wanted to show whether or not there is some tension in quasars, and in this last paper that was published in Physics of the Universe, of the Dark Universe, we found out that there is some fluctuation for the value of omega m that can point out also to this dark energy evolving models. But I think my time is up, and so I would like to thank you for your attention.
Thank you for this talk. Yes, you show a trend on the Hubble constant tension with redshift. So is the explanation for this must be physical. So is this like, or can it be systematic, like the supernovae in some way they are having some strong systematics, or is it like more evidence for intention being physical?
So we left the paper to open questions also for the community, so we gave two interpretations. The astrophysical interpretation could be that there are still hidden selection biases, for example, redshift evolution of the stretch and color that could be happening, and they are not yet fully understood or taken into account because the analysis has been done up to redshift 0.8 with the simulation, but actually we have supernovae that now are observed up to redshift 2.9 with James W. Webb. We have two cases of very high redshift supernovae, so if with the Roman Space Telescope there is this 100 nights of supernovae, if it is funded, we can have many more supernovae high redshift, and I think we are going to answer this question about the astrophysical point of view. From the theoretical point of view, we can actually open up the window to the theory of modified gravity, and we have tried a few. So some of them, they work, so there is also this other possibility. So of course, the more exciting it would be the new physics, the more boring maybe it's the selection bias, but I'm open to both of them.
Okay, and if the modification, like to describe accurately this trend, if it's new physics, does this need to be only in late redshift or also the early universe as well?
So for the moment, the analysis that we did was only to supernovae 1A, up to the redshift of supernovae 1A, yes. But in principle, we should have theory that would unify multiple probes.
So with this master sample, but H0 is determined by the absolute magnitude. So is that a free parameter that you fit, or because all the rest, all this high redshift, that's after you determine the absolute magnitude, right?
Yeah. So the high redshift probes, we use the fundamental Pantheon relation and the other relations that are in literature, and we don't use this absolute magnitude from supernova. So we can, of course, if we calibrate, we did actually two methods. We did either the calibration at low redshift supernovae. So in that case, we take the sample that overlaps in the same region of redshift with the supernova. Then we calculate the parameters of the relationship. We correct for revolution, and then we extrapolate those parameters at high redshift. So we do not calibrate, then we are completely free from any previous calibration, and all parameters of cosmology are let to be free together with the parameters of the relationship. Instead, in the other paper about the master sample, we actually evaluate the value of m, that it is the one we take the value of m, that it is the one that it is pertinent to the sample, because we did this 4-sample analysis. So whatever it was published in the original release, we are going to take that value. And if we would like to change the analysis with other models, for example, W0, WA, CDM, then we are going to compute what it is the value that it is pertinent for this other model.
Let's thank Maria again.
Thank you.